Okay, so welcome to fourth lecture. Today I am going to talk about countable sets. So probably you might have forgot about sets also, right? So very quick 2-3 minutes overview again about the set, and then we'll talk about countable set, and then we will see the beauty of real line. Okay, so you can see how beautiful it is, and then I think that much will be sufficient for today. Then in the next class, we are going to start with special kind of functions which are known as sequences. Right? I think you know about sequences, but we will do few experiments with sequences, and you will see how that idea of limit of a sequence will emerge. Okay, and that's really pretty interesting thing. So anyway, so before starting a countable set, again I have to probably last time we were not able to write anything, right? So if you remember, I'm just going to rewrite it again briefly. Our number system was n is equal to 1, 2, 3 natural numbers extended to integers, which is 0, plus minus 1, plus minus 2, and so on. Then it extended to rationals of the form p by q, such that p and q are integers and q is not equal to 0. Then we extend to real line consisting of rationals and irrationals numbers, right? Then we extend it to C, A plus IB, such that, A plus IB, such that A and B are reals and I is equal to square root of minus 1. This implies that I square plus 1 is equal to 0. 0. Right, so you know about these facts. So as I mentioned, for each cases, there were equations which we could not solve, and so we need to extend. For example, on n, if we have equation x plus 2 is equal to 0, we don't know how to solve it. So we extend it to integers. Then there are equations like 2x is equal to 1, we don't know how to solve it, right? So we extend it into rationals, right? And then there are equations x square is equal to 2, we don't know how to solve, so we went into reals, right? And then there are equations x square plus 1 is equal to 0, which has no root, no real root, right? So we extend it to the complex. And as I mentioned, complex is known as splitting field. So Q, R, C are the three examples where we can do all the operations of addition, subtraction, multiplication, division. So these three things are known as field, whereas the other two are not field, right? It's very, very basic thing. Now, can we extend it further? Well, you may say that if the equations we are able to solve, then why do we need to extend? But you see, mathematicians are always having curiosity, right? So there was a mathematician, Hamilton, who used to eat potato chips quite a lot, actually. And he used to, after eating potato chips, he has extended these things to further, extensions. So for example, hypercomplex numbers. 1ijk. A number is combination of 1i. So here in the complex, number is combination of what? A into 1 and I. So 1 and I. Right. So A times 1 plus I times B. There it will be A times 1 plus I times B plus J times C plus K times D. Where I square is equal to minus 1, J square is equal to minus 1, K square is equal to minus 1. Hypercomplex numbers. Right. And a lot of other interesting things are there. Even people have come up with what is known as Clifford algebra. Beautiful stuff. And wonderful applications everywhere, right from quantum computers to wireless communication and to protein-protein interaction, okay, in biology. See, so whole world is mathematical, and these rules are written in mathematics, right? So as long as you understand these number business, right, you have the command on different things, right? So, so I think, I mean, you can see what, so you can probably try to see what are the hypercomplex numbers, why do we need them, of course. So you can define the multiplication, addition in the same manner, keeping in mind that I square is equal to -1, j square is equal to -1, k square is equal to -1, right? Those kind of things. Anyway, so this is a very basic scenario. So we are going to do calculus on this and this. Okay. We are not touching Q. For of course, you will observe that Q is very, very dense. So actually, I will summarize that two beautiful things to know about these number systems. First, that of course, QRC are playing grounds where we can play with addition of subtraction, multiplication, division, which is very good thing. Number two, Q has holes. But when you draw the real line, there is no hole. Okay. So if you walk on the Q, a line of rational numbers, suppose there is a hole, you can, go inside the hole. But on the reals, there is no hole. And what do you mean by no holes? I'll actually give you in the form of some facts, and you can enjoy proving them over a cup of tea, right? So that is next thing, right? So let me start. So this is the summary basically. Right? It's very, very important thing to remember. On real line, there is no hole. Okay. And on Q, there is a hole. Okay. I'm thankful to Professor Bush. I'm using his slides with permission. It takes some time to make the slides, but anyway. So this will give you a quick overview in 2 minutes, because this is all these things you know. The flash will be sufficient for you. Set. What is set? So what is the definition of set? Set is a collection of elements. No, that's the wrong definition. Set is a collection of well-defined objects. So here comes your first tea time problem. Give an example of a collection which is not well defined. Understand what I mean? Set is a collection of well defined objects. So give an example of a collection which is not well defined. What do you mean by well defined? I should tell you what do you mean by well defined. Well defined means if there is a collection is given to you and you find some element, you can precisely say it belongs to this collection or not. If you can say for surety, then it is a well-defined collection. Otherwise, it is not a well-defined collection, right? So first tea time problem, give a collection of objects which is not well-defined. Okay? Got my idea? From as soon as you start with set theory, problem starts, right? Tea time problem starts. Okay, right, good. Then you know all these things. Collection of objects, well-defined objects anyway. Universal set is there and all those things you are reading from this high school. You can do all kind of operations, union, intersection, difference, offsets, right? Complement, just take the complement with respect to the universal set. For example, complement of even integers is odd integers, right? In the integers, if the universal set is integers. De Morgan's law, very famous. I think you know all these things. Then we have empty set, which has no element, right? So union with S will give you S, intersection will give you phi, because whatever is common. S minus phi is S, phi minus S is phi, and so on. And phi complement is a whole universal set, right? These are the very high school things you must be knowing. Now comes another beautiful thing. Subset. So A is a subset of B, right? If A is having 1, 2, 3 elements and every member of A is a member of B, then A is a subset of B, right? Very well-known fact. Then there is something called proper subset. If A is strictly subset of B, right? So basically number of elements here will be strictly less than number of elements in B, right? Now beautiful question comes here. We know the set of integers. How many of them are there? Infinite, right? and even numbers, set of even integers, 2 times z, all even numbers. Even numbers are subset of integers, right? Now both have same number of elements, but one is subset of other. How this is possible? See the beauty. Why they have same number of elements, I can tell you. There is a function f from here to here, which is f of n is equal to 2n. This function is 1 to 1 and onto. Right? That means once you give me an even number, I can give you integer. For every even integer, I can give you integer. So for every even integer, I can give you integer. So there is a 1 to 1 correspondence. So that means the number of elements in even 2z is same thing as in z. Right? Agree to this point? But one is a subset of other. So that beauty you can enjoy on a cup of tea and explain to me why. Any idea, by the way? It's a very easy thing, that's why. Any idea in the class? Why? Yes.
So according to me, infinity is not a quantity, it is just a symbol with two defined uncountability. So it is not a number, I think.
As I mentioned, there are different kind of infinities, so you can compare. So then, by the way, have you heard of Hilbert Hotel? Hilbert Hotel is a very popular example which can give you a feeling of what is infinity. So suppose there is a hotel consisting of room numbers from all natural numbers, suppose, right? 1, 2, 3, 4, and so on and so forth, right? And all rooms are filled. None of them is vacant. And there is a marriage bus with 100 people arrives at the hotel. And they say that we want room. All the rooms are filled, right? There is nothing, no vacancy. Then the manager was, if you say he was a Hilbert, so he said that it's very easy. Ask everyone to shift 100 rooms, next to their room, right? So everybody shifted and these 100 people went inside. This is possible because number of rooms are infinite. See the beauty of Hilbert Hotel, right? So this infinity business is, quite beautiful. You can enjoy, right? So because 2z looks like a proper subset, right? But since these are infinite things, this A is subset of B, does not, so number of A, so number of elements in A is strictly less than number of elements in B, is only for finite. And this is the infinite case, right? The things are different. Got the first punch of infinity, right? So this is what infinity business. Functions, by the way, right? Function is a rule associated with every member in a set A, giving unique image in another set B. All these definitions you already know, right? Then disjoint set, cardinality of A means number of elements. Power set, it's very, 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 very useful concept in computer science. If S is a set A, B, C, power set is set of all subsets. So 2 raised for S is the notion that they denote it. Okay. So if there are 3 elements, there are 8 elements, right? 5, A, B, C, all elements with single element, 2, a combination of 2, and then finally 3. Another beautiful thing about power sets, that each element of power set you can represent by binary numbers. See, for example, here, if I say this is position 1, position 2, position 3, so this means 0, 0, 0. Neither there is A, neither there is B, neither there is C. This means there is A, no B, no C. This means there is only one B, right? And this is, and like that. Finally, you have 1, 1, 1, right? So power set elements can correspond to binary strings. Beautiful thing, because you will see that I'm going to show you something with this, right? In computer science, this is very, very important thing, right? Power set idea. Okay. Cartesian product, A cross B, all these things you know. Functions. By the way, so function is a rule associated with every member of A giving unique image in B, right? Any subset of A cross B, will it be a function? No, it is called a relation, if you remember, right? So, see, a lot of interesting things can be asked. If, as you know, what is one-to-one function? A function is one-to-one. If f of B is equal to f of A implies that B is equal to A, right? Then the function is one-to-one, right? So a natural t time problem that can be asked, how many one-to-one functions are there from a set of size m to set of size n? ये सारा मैं दे रहा हूँ, right? And it may come anywhere in the exam or in quiz. So you have to solve it, right? How many one-to-one functions are there from a set of m elements to set of n elements? A set, so domain has m elements, codomain has n elements. How many one-to-one functions are there? These are interesting interview questions as well, by the way, right? So, how many one-to-one functions are there? So, one-to-one functions means injective function, they also call. Onto function, when image set is whole codomain, right? Onto function, right? So, one can ask, so they are known as surjective function, right? Then one-to-one and onto function means bijective function. I mean, these things are you already know. Now, using these ideas about bijective functions, I'm going to define what is known as countable set. Why do we need the definition of countable set? So countable set, so this class is countable because there are finitely many elements. I can count. So with finite, there is no problem. But if there is infinite set, then question comes, can I count all the time? Need not be. Sometime you can count, sometime you cannot count. So when I'm counting you, I'm just, what I am doing? 1, 2, 3, 4, 5, 6. I'm associating natural numbers with each of you, right? Attaching a natural number. So this attachment mathematically is known as there exists one-to-one and onto function from set of natural numbers to this class, right? If it is an infinite set, the same definition works. If there is a one-to-one, sorry, so finite case anyway you can count. I'm talking about in terms of infinite set, right? So infinite set, infinite set is countable if there exists one-to-one and onto function from set of natural numbers to that set. Okay, then we say that that set is countable. So essentially, if somebody asks you that show that this set is countable, you have to produce a one-to-one and onto function f from natural numbers to elements of that set. Okay, if you are able to do that, then you are done. Okay, now let me show you some examples. So infinite sets are either countable or uncountable. This is something you need to keep in mind. Finite sets are always countable. Infinite sets are either countable or not countable. So countable sets, if there is a one-to-one correspondence between the elements of set and natural numbers, right? As I mentioned, right? 1, 2, 3. So if you give me natural numbers, so natural number set is countable. The first example that I gave you, capital N, is countable, yes. You give me one, I'll give you another one. Same, the one-to-one correspondence, right? So this is countable. What about set of even integers? Set of even integers is countable, right? You give me one, I give you another natural number. You give me another even integer, I'll give you another natural number, right? So one-to-one correspondence you can find because f of n is equal to 2n is a one-to-one and onto function, right? So that is countable, right? So basically every element of set is mapped to a number such that no two elements are mapped to the same number, right? This is the key thing. Now, the set of even integers is countable. There are different ways you can see. If you include 0, the function will be a little bit different, but otherwise, you can do that. Very good. What about set of rational numbers? You just saw rational numbers, P by Q form. Are they countable? Are you not afraid of saying yes? Because there is a very nice t-time problem available there, right? So you see what happens. Okay, how do we count? 1 by 2, 3 by 4, 7 by 8. You see. So set of rational numbers is countable, but how? If our approach is okay, 1 by 1, 1 by 2, 1 by 3, and so on, and you associate with 1, 2, 3, there will be a problem. You will not be able to encounter every number in this way, right? So there will be a problem like, it will never count 2 by 1, 2 by 2, 2 by 3, right? So a clever trick is that you arrange these numbers in the form of a array, okay? And then you see, you can count. This is the better approach. 1 by n, 1 by 2, 1 by 3, 1 by 4. I'm assuming initially positive, right? And do the negative things as well. So 1 by 1, 1 by 2, 1 by 3, 1 by 4, 2 by 1, 2 by 2, 2 by 3, 2 by 4, and so on, 3 by 1, 3 by 2, and 4 by 4, like this. You arrange in an array. Now counting, I can start from top one. 1 by 1 first, then 1 by 2, 2 by 1, then 3 by 1, 2 by 2, 1 by 3, like that. We can keep on going. Circular car, right? So you can count. So here is the approach. This, like that, you can count, right? Now, positive things will be counted. Like, you know that this will never leave any positive rational number out. So what about 0? So you can start with 0. You place 0 here. Okay. So first you do that, and then you do counting like this. Then you will say, what about negative rational numbers? You insert negative numbers between these positive numbers, and then you again do the similar thing, right? So you can count. So essentially, this ensures you the way of drawing that you can count rational numbers, right? But beauty is not here. Beauty is in finding that one-to-one and onto function. I can give you some hint to see that these numbers, how we are counting. 1 by 1. So there is P by Q form, right? So numerator and denominator sum is how much? 2. So some association with 2. 1 by 2 and 2 by 1, association with 3. 1 by 3, 2 by 2, 3 by 1, association with 4. Right? This is known as height of the number kind of thing. So using this kind of technique, design a function which maps natural numbers to all these rational numbers to natural numbers. That is a nice tea time problem. Finding that one-to-one and onto function. It's a non-trivial task. But beautiful way, you 2-3 cup coffee lagega, right? Sit down in the evening and try to find that one-to-one and onto function which maps rational numbers to natural numbers. Any question at this point? I mean, you should ask, yes. No, we are not counting 2 times. I am saying that there is association. It seems to me that kind of association looks like is making sense. That's not the actual function. You need to find the function. I am saying that. I'm giving you a hint, an idea to think. Okay. Some sort of association looks like connecting to the natural numbers, right? As a height of the function. So can I do something with this, right? Okay. So the question is, so I have to show that rational numbers are countable. I told you the way how to count, right? You have to find a one-to-one and onto function from natural numbers to rational numbers, or rational number to natural numbers, right? Which is one-to-one and onto. You have to find that function. Because that will 100% say that yes, it is countable now, everything is fine. But although I am able to convince you in a loose manner, but that is a more mathematical statement, right? You are a mathematician? Okay, good. So you can do that, right? Okay. Now uncountable set. So there are different ways. I mean, there are different versions of the different problems which we will show you. That I will show you one problem, and probably I'll give you a hint for the other ones. But as I mentioned, to show that something is not countable, that person who did a lot of magic with infinities, Cantor, George Cantor, he actually developed one argument, which I'm going to show you. Beautiful argument, right? To show that something is not countable. Okay. And this argument you need to master. You can apply in for any thing. If you want to show that something is not countable, you have to use this argument somehow. Okay. So at least master that argument. Okay. So I'll show you this with an example. So a set is uncountable if it is not countable, right? So this is the result which we are going to prove, that if S is an infinite countable set, if S is an infinite countable set, okay, its power set is uncountable. See the beauty? S is infinite, countable, but its power set is not countable. Okay, and it is this fact, a very, very powerful fact, by the way. Using this fact, you can show that computer science has a limitation. Turing machine has a limitation. I mean, normally I do this in discrete math class. I mean, some of the lectures are available. You can watch that there. You know, that Turing machine has a limitation. That's why people become, they started believing in God. Computer science has a limitation, means, you know, we are having a limitation. So obviously there is a limit to the reasoning, or there is a limit to the mathematics. And essentially you started believing in God, right? You'll become bhakt. So basically, this is a beautiful statement. So that's why I'm giving you this example. Okay, if S is a infinite countable set, its power set is not countable, right? So what I'm going to do, I will take the power set, okay, and you know that each element of power set corresponds to a binary number. I just showed to you, right? They are binary numbers, right? Yes. Any question? Yeah. So I'm going to do the proof right now. So the proof goes like this. I mean, the idea of the proof goes like this. I will assume that suppose power set is countable. Suppose countable. This is the, you know, method of contradiction. Then, if I assume that the power set is countable, I will list element one by one. Element number 1 map to 1. Element number 2 map to 2. Element number 3 map to 3, and so on. Right? I have assumed that it is countable. I am listing all the elements. Then I am going to produce an element which, using Cantor diagonalization argument, which is not in the set. I mean, which is in the set, but which is not in this list. That means our reasoning has some problem. You understand what I mean? I will assume that, थोड़ा ध्यान से सुनना, ये बहुत important बात है. I will assume that the set is countable. Power set is countable. I will list all its elements. पहला element corresponds to 1, second element corresponds to 2, third element corresponds to 3, and so on. Right? So that means it should have all the elements. Because obviously, you know, power set के सारे elements इसमें list होंगे, right? Now what I am going to do, I am going to produce, using Cantor diagonalization argument, one element which is member of, so which is a power set element, but which will never appear in this list. Okay, and so our assumption that power set is countable is wrong. So everything boils down to producing that element which is not in this list using Cantor diagonalization argument. So let me show you the magic. Beautiful magic, right? See. So suppose S is countable. I mean, of course, S is countable, right? We know that. So we can write its element as S1, S2, S3. This is infinite countable set, right? I can write down elements S1, S2, S3, so on, whatever. These are elements of F. And each of these elements, so elements of the power set will be of the form, say phi, some members of these SIs, right? And each of them corresponds to binary numbers. Okay? Binary strings. So these are the, so binary encoding. S1, power element S1 is 1, 0, 0, 0. S2, S3, those are ones, others are 0. S1, S3, S4, Those are 1, others are 0, like that. This is absolutely clear to you. Every power set element corresponds to a binary string, because we are going to use this fact. Okay? Fine? Very good. So each element of the power set corresponds to a binary string of zeros and ones. Right? This is the thing. And if binary string is given, I can always corresponds to which element it is there, right? Based on the positions, right? Say that this is the element of the power set, right? So binary string corresponds to element of the power set element corresponds to a binary string. This is the first observation. Next, now we are assuming that suppose the power set is countable. Okay? As I mentioned, suppose the power set is countable. Now that means we can enumerate the elements of the power set. This is our power set. So set S had element S1, S2, S3, and so on. Suppose here the elements are T1, T2, T3, and so on. T1, first element, T2, second element, T3, third element, T4, fourth element, T5, fifth element, and so on. These are the elements of the power set. Right? Now, we know that each of these Ti corresponds to a binary string. Right? Each of these Ti corresponds to a binary string. So I'm writing them. These are some binary strings. I don't care what are their values, right? I'm just saying that these are the binary strings. T1 is this, T2 is this, T3 is this, T4 is this, like this. Right? Any problem up to this point? Clear? Very good. So now these are the power elements and they are the corresponding binary strings. Now the magic comes. I have to produce, so basically I have assumed that the power set is countable. I have listed all the elements as a binary strings. Now I am going to produce a element of a power set which will never come into this list. And how do we do that? Yes, any question?
And change the ones to the zeros and the zeros to the ones.
Very good. So that is a way here. So I will take an element, I will produce an element T, I would say that element of a power set. And what I can do, look at T1. That's why it is known as Cantor diagonalization argument. I look at the diagonal of these array. The first element of this will be complement of 1, which is there, which is 0. Right? Look at the second element here, it is 1. You produce the second element of that power set element will be 0, then 1, and then 1, and so on. Right? So here is the trick. So take the binary string T, which is complement of all the diagonal elements here. So you arrive at this. This is the element of a power set. Agree? Because every binary string corresponds to an element of a power set. Fine. But this T will never appear in this list. Do you agree to that also? The way of we constructed, right? T. Because it will always differ in that particular diagonal element, right? Suppose T is equal to Ti. Suppose T is equal to Ti for some I. We are listing T1, T2, T3, T4, and so on. Suppose T is equal to Ti for some I, but then it will differ at the ith diagonal entry because of the way we constructed T. So this will never appear in this list. So our assumption that the power set is countable is wrong. Got it? Any question about this very beautiful idea? And you can apply into all the problems of uncountable sets, this diagonalization idea, very beautiful idea, right? In fact, once you say that one set is uncountable, sometime you try to find one-to-one and onto function with other set, and this set is also uncountable. And anyway, so what is basically key problem is this, choosing this string. Okay. Now, yes. Okay, what do you not understand here? So I'm saying that, so you understood that we are listing the TIs, elements of the power set. Now I'm producing a string T, which has every element. The first element is complement of the first element of T1. Second element is complement of second element of T2. Third element is complement of the third element of T3. And T4 is, basically here the fourth element of T is complement of the fourth element of T4. Like that we can continue, right? So this string will never appear in this list, right? Right. But this is an element of a power set because every binary string corresponds to a power set, right? Okay. So that means there is a contradiction, right? So that means we are able to produce. So we assume that this list is countable. Every element should be there in this list, but there is a string which is not there in the list, right? Now, similar argument when you want to use it for now other examples. Open interval 0, 1. Is it countable, uncountable? Uncountable. So what you do? You write down the binary. So assume that it is countable. Write down the decimal expansion for each of those numbers, right? First number T1 as 0 point, whatever, B1, B2, B3. Second number 0 point, 0 point, C1, C2, C3, like that. You can keep on doing this, right? Binary decimal expansion of the numbers. Then again produce a number which is between 0 and 1 and which differ at the diagonal element. Now there, rather than taking complement, you can take anything. So for example, if that element is 5, you can take 10 minus 5. If it is 6, you can take 10 minus 6, right? That will create that Cantor diagonalization argument. So that way you can show that that open interval or the closed interval 0, 1 is uncountable, right? That is a similar. Now similarly, you can show it for the real line also. Real line is also uncountable. Right. These are all examples you have to use. I have taken very simple example. Okay. Now you using the similar idea. The only thing is you need to worry about how to choose this diagonal element, right? If it is basically, because in the real analysis when we are doing this, we are looking at the decimal expansion. Okay. At decimal expansions, numbers are from 0 to 9. You take anything other than whatever number is there. You take, I mean, you can define some rule, right? Which will make sure that whatever there is, it is there, you subtract it from whatever number you want, right? So something like that, right? And you can continue. So this is the key idea about the Cantor diagonalization argument. So this binary string corresponds to this power set element, which is not there in the set, right? Okay, so power set is uncountable. Very nice. I think this was a major thing today. Now we can do some small warm-up things. Now we look at the real line. As I mentioned, you need to believe that there is no hole on the real line, right? What does that mean? I'll write down 3 facts about the real line. By the way, another T time problem. The set of all rational numbers in closed interval 0, 1 is countable. If you fix an interval and look at the rational number, they are also countable. Okay. Okay, now I think there are certain properties which I think you should know on the real line, which I am mentioning. Bounded above. So basically, this is our real line. And the concept of bounded above. So suppose A is a subset of R. Okay. Then we say that, okay. We say that A is bounded above if there is a number n, there is a number n in R such that for every x in A, x is less than or equal to n, right? So basically it is saying that on the real line, there is a set, it could be here, say this is A, right? And if there is a number n, which could be here, right? Say this is number n. So all element here, if x is an element here, it will be less than n, right? For our, so basically we are saying yes, a set is bounded above by some fixed number, right? Similarly, you can talk about bounded below. So I'm not doing that, right? You can talk about bounded above. There could be a lower bound also similarly, right? For some set. Now we say that a set is bounded if there is a, it is bounded below and bounded above. Okay. So something called bounded above, something called bounded below. A set is said to be bounded if it is bounded both upper side and the lower side. Then what is known as, so for example, what about the set of natural numbers? Is it bounded below? Bounded below. It is not bounded above, but it is bounded below. One is there as a lower bound, right? I mean, you cannot go more than one, right? So it is bounded below natural numbers. So n is it bounded? N is not bounded, right? N is not bounded because it is only bounded from one side, but not the other side. What about closed interval 0, 1? Is it bounded? Very good. Now I can say that. Now tell me whether this statement is true or false. Lower bound of n is -7. True, right? Because 1 is the anyway the the cut, and then after that take any number, right? That will work. Okay. Now when we talk about, so this is one number which is so A is bounded above by this number. There could be another number here, maybe say n1, right? Could be another number here. So there could be something which is very close, right? So that will be known as least upper bound. Or, right? Yeah, sorry. Greatest lower bound. Greatest lower bound, right? Let me take an example so it will be very clear. Suppose B is half 3 by 4, 2 raised power n minus 1 divided by 2 raised power n, and so on. Can I say that what is the greatest lower bound for x belongs to B of x will be how much? Huh? One by 2, because this is the lowest, right? Greatest lower bound, right? Now 1 by 2 is in the set, which is okay. But what about least upper bound of x when x belongs to B? 1, because you can take the limit as n tends to infinity, right? What happens? That's very good. What about the greatest lower bound of n? 1. Very good. And least upper bound of 0 is same thing as 0, right? Greatest lower bound of 0. I think these concepts you know already. I'm just recalling, right? So a set is bounded if it is bounded above and bounded below, right? There is least upper bound, there is greatest lower bound. Those kind of ideas are there, right? Something which is very close on either side. And so we can find, given a set, we can always find out these things, right? Fine, clear. Very trivial thing. Now I'm going to mention those facts actually. We have time, I guess we can mention that. Fact 1, although it is known as Archimedean property, I don't worry about what property it is known. It is something, if x and y are two real numbers and x is positive, there exists a positive integer n such that n times x is greater than y. Looks like okay to you, right? But can you prove it? I have circulated a reading material, right? I am writing only those facts from there, right? You can look at it, right? If x and y are two real numbers, of course x is positive, so right hand side of the zero, right? There is a positive integer n such that n times x will be greater than y, right? So it is saying that if we have this is 0, this is x, suppose, and this is y, then we can find an integer n such that n times x will be bigger than y, right? Which is very obvious fact, right? You use it, but you can you prove it? Now, fact 2. Suppose x and y are two real numbers. Okay, some distance apart. So in between there is a rational number. If x and y are two real numbers, so it says that if x and y are two real numbers, now these real numbers could be rational, irrational, whatever, I don't care. There is always a rational number in between them. This is density of rationals. This is the property of density of rationals. Between any two real numbers, there exists a rational number. Okay. And another one, fact 3. Somewhere here, or whatever, anywhere, there exists irrational number also between x and y. So this is density of irrationals. Between any two real numbers on the real line, there exists a rational number. And between any two real numbers on the real line, there exists an irrational number. So essentially, it says that there is no hole on the real line. Actually, set of rational numbers is tens in the real line. That means if we take a sequence of rational numbers, it will converge to a real number, which could be, I mean, I'm saying that it could be rational, it could be irrational. But on set of rational numbers, you cannot do this. So rational number set has a hole. Real line does not have a hole. That is a very, very loose sense. I am giving you an idea that on the real line, there is no hole. Okay. Got it? That is the whole summary of today's lecture. Real line is dense. So basically, rational numbers are dense on the real line. This is the statement you should remember. Rational numbers are dense on the real line. That means if you take a sequence of rational numbers, it will converge to a rational or irrational, right? For example, if you take 1, 1.4, 1.41, and so on, that will converge to square root of 2, which is an irrational number, right? Okay, so I think this much is enough. As I mentioned, pura Mahabharat likha ja sakta hai real line pe. You can, if you are very much excited, you can read about it, what is Denikin cuts and so on, that those great mathematicians, right? Actually, अगर आप नाव लेकर के निकलो रियल लाइन पे, आपको wonderful things मिलेंगी. Sometime I will show you also, but we have to finish everything in a balanced approach, right? So this much is for today. Next class, we are going to look at the sequences and we'll take the idea of convergence. Okay. एंड कर दो नहीं तो हाँ ब्रॉडकास्ट होता रहेगा हाँ बताइए